it's a constant, derivative of constant 0. Anyways, back to the chain over here. Derivative of 2x is 2 multiplied by 2. And look what we got. 2's cancel. Back and restart it. Secant squared of 2x, which was the original problem after we morphed it into secant squared of 2x. It started as 1 over the cosine squared of 2x. And there you have it. Solved and proved our last book example. Now we're moving on to... Alright, here we go with example number 6, also known as the good stuff. This is where it starts getting pretty interesting. When you first look at this, you're just like, oh, it's just tangent. I mean, what can a little tangent do? But it's actually very tricky. And AP exam, I talked to Ms. Masson. They say that she says that they like to do this. They'll give you functions such as tan or cotan, and you'll be puzzled about what to do. All you got to do is change tan into what we also know it as. We know that tangent is also sine over cosine. It's pretty. Now it's actually solvable using substitution, and this is where it gets kind of hard and tricky because you got to figure out what do I choose to get to set as u, so that this function becomes a nice little function that we can easily get the integral of. And in most cases, we're going to take the denominator instead of equal to u. We do this because the derivative of cosine, like when you have a tangent, the derivative of the bottom, which is always cosine, is going to be it's the opposite of sine. So you're going to end up with sines, both signs there. And the reason why it should always be like this, even if you have cotangent and you change it into cosine over sine, you set the bottom equal to u sine, and you get the derivative of sine is cosine, and it allows us to get a 1 over something, which we easily know as natural log when we take the antiderivative of it. So we set u as the cosine of x, and the derivative of this is negative sine of x dx. And now let's just plug in. I like to change this to 1 over cosine times sine. You can do that in your head, or you can just, I guess I'll write it out real fast. 1 over cosine x times sine x dx. This just helps me be able to see this for when I plug in my u. So we'll say that this is equal to 1 over u. Again, let's just plug in our cosine of x equals u. Multiply sine x dx. Well, let's see. We have negative sine x dx. So what can we do to what can we do there? Just simply plug it in and change this to negative, and write du. So now we have negative 1 over u du, and it's fairly solvable. So what do we do when we have 1, say 1 over x? If you can see that over there. Yes, you can. Then left corner, 1 over x. Antiderivative of that is ln of x. So this is what we want to be going for here. We want to be looking for something like this. And, well, we can't really do much. We have negative 1 over u. But then we look back to our constant multiplier rule, and this negative 1 is just, really, we can take it out here and put a negative 1 times this, and it's simply constant multiple. So you put the negative sign out front, do your integral 1 over u du, and now it's pretty solvable. Keep our negative sign here. The antiderivative of 1 over u is, like we said over here, ln of u, but you better put your absolute value bars there or you'll lose the point. And then plus a constant. Don't forget that. And now let's plug in what we have as u, keep the negative out. The opposite of the natural log of the absolute value of u. You have to dig way deep here and realize that this is actually 1 over the natural log of the absolute value of u. And plug in what we know. Plus c, of course, not e, c. And now it's 1 over the natural log of cosine of x plus c, which is equal to our final answer of the natural log 1 over cosine is simply, say it with me, secant. And here we go again, out of board space. The big plus c, so you won't forget. Natural log secant x plus c. So, much harder problem. Much harder. And they're only going to get harder from here. So, let's just try and move forward. And hopefully conquer some of these integrals. I mean, next example I'll do a definite integral of the same form and show you how we can solve answers, and pretty much that's all there is to this section. We got one more thing to go over. It's just separating your variables. It's kind of intense, so I'm not gonna go over that. If you guys really want to special request it, I will do it, but I can't say for certain if we're going to go over it in class or not, so I don't want to teach you something that you don't need to know. So I'll do one more example, doing it with a definite, plugging in some numbers, and then move on to 6.3. Alright, last example of 6.2, we're going to do a definite integral using our substitution that we learned. I found this example in the book again, and it's very good. I like this one. It looks like a very daunting problem, but there's actually a little trick that we can do with definite integrals to get an answer quite quickly. Instead of fully substituting everything in, we're still going to set our u, we're going to set it to be tangent of x, and we're going to say du is equal to secant squared of x dx. So this whole thing right here becomes du, and this becomes u. And what we can do from this is we can notice that u of 0, if we were to do u of 0, because this changes into, u du once again, 0 to the power of 4. We notice, I'm going to do it at the top, that when we do the fundamental theorem of calculus, part 2, we find out that u of 0, or I guess we can do u of pi fourths first, just to keep it in order of our fundamental theorem. U of pi fourths, simply plug in pi fourths to u, so tangent of pi fourths is simply 1. And then we can also do our lower limit of integration, u of 0. Plug in 0 for x in your u function, which is tangent. Tangent of 0 is 0. So then we can come down and say that now we have our new limits of integration. Because we're changing this to u, we have to also change our limits of integration based on our u function. So once we get our new limits of integration, we simply change it to our lower limit, which changes into, it's still 0, just a little phenomenon there, but our top limit of integration, pi fourths, changes into 1. So now we have 0 to 1 u du. And from here, simply do a power rule for integration. Just add 1, 1/2 u squared, or u squared over 2, however you like to write it. And we don't add our constant here because to indefinite we have limits of integration. And then you simply just plug in your limits, and we'll do 1/2 times 1 squared minus 1/2 times 0 squared. And we get 1 squared is 1, 1 times 1/2 is 1/2. 0 squared is 0, 0 times 1/2 is 0. So our final answer is 1/2.